Hello, my name is Isabel Parra, and my research this summer was on examining lithium-ion transport through a liquid and amorphous multi-component film. I'd like to thank our sponsors, CREDS and TAMU ORAU program. This work was supported by the Department of Energy, National Nuclear Security Administration under award number DE-NA0003857. I'd like to thank my mentors, both from Texas A&M University, Dr. Perla Valbuena and Francisco Ospina Acevedo. So the motivation of my research was to build both hard and soft skills as an engineer by using different software that I'd never been exposed to and making presentations and being able to present them efficiently, as well as helping advancements in battery technology as a response to concerns about the usage of fossil fuels. The goal of my research has been to analyze a multi-component film formed when lithium metal is exposed to a liquid electrolyte containing certain lithium salts dissolved in a solvent. In particular, we're interested in characterizing how the lithium ion diffuses from the solid metal into the liquid phase and when the film is formed into the amorphous phase. The methods for my research have been using the HPRC supercomputer facilities, LAMPS program, the Materials Studio, and Oviedo. Within these, I've run multiple molecular dynamics simulation jobs with the supercomputer facilities, and I have analyzed different aspects of those jobs and jobs that others have run to see how the atoms and molecules interact with each other and behave within the system. So at the beginning of the research, I was given two systems to analyze and compare. I was given lithium hexafluorophosphate with a DME solvent and lithium triflate with an EC solvent. This is the lithium hexafluorophosphate, and as you can see here, there is a more liquid composition, which is the electrolyte, and the more structured composition, which is the lithium slab. So for most of my research, I have been mostly looking at what's called the knockoff effect that happens in this system. And the knockoff effect is where there is an exchange of position among lithium atoms of different layers that allows the lithium atom to fusion to the top of the electrolyte base. To keep track of this, I have color-coded the lithium slab so I can tell which atoms started where. So in these systems, the atoms at the bottom are less oxidized, which means their charge is going to be closer to zero, while the atoms at the top of the slab are going to be more oxidized, which means their charges are going to be more positive or closer to 1. Now the diffusion of these atoms in the lithium slab are going to be affected by the different molarities that I'm about to show you. So here I have the beginning of all of the systems that I've color-coded with slight changes in the electrolyte or the gray area because of the different concentrations. But this is how they all begin for the most part. Now in the original system of the lithium triflate with the EC solvent, I was given an already created system and job, and the ending looked sort of like the picture on the left. Now they asked me to continue that and add more time to it, so I ended up with something like the picture on the right, which you can see has a more mixed colored look with the atoms exchanging position and going higher up into the electrolyte base. So here I have a system that I made with a molar concentration of 4. So that means that I have a higher molarity and higher or more molecules of salt per liter in the solution. So the original one, this one, had a molar concentration of 2, while this one has a molar concentration of 4. And as you can see, the diffusion of the colors and the mixture of the colors is much more intense here than it is in the original one, with the colors kind of going crazy and going everywhere, with only really the purple, pink, blue, dark blue colors sort of staying at the bottom, and the rest of them go all over the system. So here I have graphed the average charge of the first 6 layers of the lithium slab for the system with a molar concentration of 4. And you can see that most of them sort of start out with a more volatile charge average, and at the end they sort of even out. Here I have the system with a molar concentration of 6, and this is what it looked like at the end of the 20 nanoseconds, which is what I did for the molar concentration of 4 system as well, 20 nanoseconds. And this one doesn't have as much color dispersion, color mixture as the other one, the molar concentration of 4. This one has more of the bottom layers intact, with the pinks, purples, blues, medium to light blues, all mostly staying where they originally started. The reds do seem to stay more at the top. Greens do diffuse sort of everywhere, as well as the oranges and yellows. And this all again is affected by the molar concentration of the solvent. Here I have again graphed the average charge of the first 6 layers of the lithium slab of the system with a molar concentration of 6. And unlike the other one, the charge here seems a lot more volatile the entire way through the 20 nanoseconds and doesn't seem to even out the way the other one does. So now I'm going to show you small clips of the systems all actively going with the simulation, just so you can see how they move a little bit. So here is the first one, the one that I was originally given, and this is how it moves. You can see it from the side as well. And this is where it sort of ends up going. And this is going to be at the end of the system that I was given initially. Now here is the beginning of the system that I had to continue from the last system. This is how it starts at the beginning of where I took over. And this is how it moves. And by the end, it looks like this. Here is the system that I created with a molar concentration of 4. You can see that the top is already diffusing, and by the end, we have a great big mixture. And here is the system with the molar concentration of 6 that I made. And it ends more diffused than the original system that I was given, but not as mixed up as the system that I made with the molar concentration of 4. So my preliminary conclusions are that we can see there's a distinct behavior between these systems with different molar concentrations, where the largest diffusion activity is observed in the system with a molar concentration of 4. This may agree with the fact that there is a maximum in the conductivity of lithium ions as a function of salt concentration, or lithium ions diffuse most at an intermediate value of concentration, and this work seems to indicate that this maximum is at approximately a molar concentration of 4. Thank you for watching. I hope you enjoyed my video.